Hey everyone, this is our second lesson on our second lesson focusing on applying rational exponents to various problems. It builds on when we first talked about rational exponents, which we'll do first, and then it goes on to some of our exponent rules. And by the end of today, we'll want to apply them to solve some new problems, like solving for values of x given these rules. So that's where we're headed. As always, I'm going to do the notes in this left column. I'm going to do these. Make sure you listen, focus, copy them down, and then over here you'll have a chance to pause the video, try these out before, and then I'll walk through them with you to review the answers. Alright, so let's dive right in. Example 1, rational exponents. So the first lesson we did, we took radicals like this, so things with a root, some kind of root. This one is the fourth root, and we rewrote them as rational exponents. So the way we did that is we took, if it's the fourth root, we put it as 1 over 4. In other words, we need 4 things multiplied together to get us back to x. So whatever the root is, write it as a fraction. As a reminder, if there's not, it's just a quick throwback, if there's nothing there, we assume that's the square root, which is 1/2. X to the 1/2, rather, it would be x to the 1/2. So that's just a reminder that if there's not a number specified, we assume it's the square root. So 2. All right, go ahead and pause the video, try out this second one, and then we'll come back together. So hopefully you've paused it. When I'm looking at this, I'm like, I want to write this with a rational exponent. I see that there's a 6th root here, so I'm going to turn that into a 1 over 6. And I keep whatever's inside the same. Here it was just an x, but it may be something more complicated, like we're about to see. All right. So that was just a basic recap. Now we're going to dive into this one, which ties together both rational exponents and the exponent rules we talked about in the last video. So first, I see this is a cube root of x. I don't really know how to work with these radicals, so again, I want to write it as a fraction up here. We know how to work with the fractions. So I'm going to start rewriting this. I'm going to keep my x here as the inside thing, and then outside, I'm going to rewrite it as a fractional 1/3, because it's the third root, 1/3 exponent. And outside of that, I still have, so I've just done this first little bit inside. Outside of that, I still have the 4th power. And then after all that, I still have another x squared being multiplied. So this doesn't seem a lot simpler, but it does get us quite a bit closer, because now we can apply some of our exponent rules we talked about last time. So if I'm looking at this, I see this is an exponent raised to another exponent, 1/3 and to the 4th. And if I remember my rules, a power raised to a power means we multiply those things together. So if I do that, it's going to be x to the 1/3, just simplifying this piece here, x to the 1/3 times 4. Think of that as 1/3 times 4. You can think of 4 as 4 over 1, which when I multiply straight across gives me 4 and over 3. So my new exponent, after I've simplified this first bit, is 4 over 3, because it's 4 groups of 1/3. All right, then I have next, I still have this x squared over here I'm going to have to work with in a second. Okay. So already this is quite a bit better. We've taken sort of like 3 things and combined it into just 2 terms with different exponents, but we should be able to go further. Both of these have x bases, they have different exponents, but we should be able to apply one of our exponent rules to combine them. Looking at this, I see they're multiplied, and last lesson we learned that when we have terms that are multiplied, we add the exponent. So I want to add these 2 things up. So I want to find out, I'm going to start a new line down here. It's going to be x to the 4 over 3 plus 2. Now the tricky part here may be remembering some of our fraction rules, like how to add a fraction to another fraction. Basically the thing to remember is we have 2 wholes here and we're adding on 4 thirds. But to combine these 2, I need to talk about the same kind of things. Like I want to have thirds, but I know how many thirds we have overall. So I'm going to start by rewriting 2 as as fraction of a whole, as thirds. Sorry, 2 as thirds. So 2, I want to write it as something over 3. So to get there, I can multiply by 3. 2 over 1 is our original fraction. To get to something over 3, I need to multiply by 3 on top and bottom. That's a total of 6/3, which makes sense. 3 goes into 6 twice. So I know 2 is equal to 6/3, so I'm going to rewrite this one more time. X to the 4 over 3 plus 6 over 3. So there's 4/3 coming from the first term, 6/3 coming from the second term. Now I can combine these. I see this is just going to give me, we have 4/3 here, 6/3 here. When we add fractions, they have to have a common denominator. They do. We combine the top terms. 4 plus 6 is 10. 10/3. So there we go. We've taken this very complicated thing and rewritten it just as one variable with a single exponent. Along the way, we had to remember a couple fraction rules, right? To multiply fractions, to add fractions to whole numbers. But we'll keep practicing those as we go through these. All right? Take a couple minutes and really take your time and work through this one. Try out example 4, pause the video. Notice that there's radicals we can rewrite. We should be able to combine things on top. We also have a division. We should be able to look back at our rules, know that when we divide exponents, we're subtracting, when we divide fractions, when we divide terms, we're subtracting their exponents. Take a couple minutes, try this out, we'll come back together and walk through it together. So hopefully you've tried it out. I'm going to start. I noticed right away that there's a radical I can rewrite. I don't like that radical up there. I'd rather have it in a fraction because I know how to work with fractions. So I'm going to start inside the parentheses. I'm going to rewrite this as x instead to 1 over 4. It's a 4th root, so I rewrite it as 1 over 4. Then I'm noticing I still have my x to the 3rd on bottom. Then I notice, well, these are an exponent raised to an exponent. When I have that, my rule says I can multiply these terms. I can think of this as 5 over 1, multiply them together. Now I have a new fraction, which is just x to the 5 over 4 over x to the 3rd. All right, that's a little better. Now I see I have this thing up here and I have this thing down here, and I need to, when we have things divided, they're being divided, I need to subtract their exponents. If we remember that this means there's this many things multiplied together on top, and there are 3 divided, so we want to take away 3 from this up here. All right, so I'm going to rewrite that as 1 now. Raised to 5 over 4 minus 3. So again, we had a similar scenario over here. We're going to have a fraction and we're adding a whole number. Here we're subtracting a whole number. But before I do that, I want to talk about common parts. We have 5 quarters here. I'd like to know how many quarters I'm taking away in 3. So I want to rewrite 3 as a fraction of quarters. Well, to get there, I'm going to need to multiply by 4 on top and bottom. That's going to give me 12 quarters. And again, we should check ourselves. That makes sense. There are 3 groups of 4 and 12, or we could go 12 divided by 4 is in fact 3. So now that I've rewritten the fraction, I'm going to kind of start one more line down here. X raised to the 5 over 4 minus 12 over 4. Again, we're adding and subtracting fractions, so it looks like we should have the same number on bottom, same type of thing we're working with. Yep, quarters. And 5 minus 12, I'd be really careful here. 5 minus 12 is going to give me x raised to something over 4. Let's see, 5 take away 12. I think that's going to be 7. Right? 7. Yep. 7 plus 5 is 12. Or in other words, yep, 5 take away. Yep, so it's going to be negative 7. Always check on a number line too, right? If I'm at 5, I'm taking away 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that puts me at negative 1, 2, 3, 4, 5, 6, 7. Yep, negative 7. All right. So again, we're able to take our knowledge about rational exponents, about our exponent rules, where we have power to a power, so we multiply, where we're dividing, so we subtract, and then we also combined it with some of what we know about fractions to come up with a much simpler expression than what we had at the start. All right. I also don't want us to get intimidated by the fractions. We're bringing them in here so we can practice with them some, but keep in mind, in general, what we wanted to do, we can still apply these rules. It won't always be fractions. We just want us to be aware that there might be fractions sometimes. Okay. The last example here is going to be rational exponents, and here we're going to start applying them to do things like, in this example, our job might be to solve for x. So in this expression here, there's something that's unknown. In other words, we need to know what exponent we could put here that would make this whole side equal to 4. As I look at it right now, though, I have no idea. Like, because it's not written in a way we're used to seeing, it's not written with fractions and with rational exponents, it's going to be very difficult to solve. So first, I'm going to rewrite this problem as a rational exponent. Cubed root, that's the third root, so I'm going to rewrite that as, oops, can't see me. Third root, you're going to rewrite that as 2 raised to the 1/3. And then outside, we still have this x equal to 4. Now, when we're solving expressions like this, we got to think pretty carefully. We know our base here is 2, and we need to figure out what our exponent's going to be altogether that's going to give us 4. Well, I'm going to start by making a note to myself. First of all, I think, well, if my base is 2, I want to know what my exponent would be to give me 4. In other words, 2 times itself, how many times would give me 4? Well, 2 times 2 gives me 4. So I know that my exponent needs to be a 2 altogether. So this whole exponent up here needs to be a 2. All right, I'm still kind of thinking through this. I'm not quite sure what to do. Maybe I'll take a couple seconds and rewrite this expression just as a single exponent. So I see I have an exponent raised to another exponent, 1/3 raised to the x. So I'm going to rewrite this one more time over here. Power to a power means multiply, so 2. I'm going to treat these both as fractions. 1 times x, 3 times 1. So 2 to the x over 3 equals 4. So all I've done is rewrite this, and I've also been thinking about in the back of my head, what do I want my exponent on 2 to be? I know this exponent has to be equal to 2. So altogether, I guess I'm seeing now, I want something divided by 3. It needs to be the same as 2. I need this exponent to be 2. So something divided by 3 gives me 2. I could do a couple things. I could write an equation. I know I want this whole exponent to be equal to 2. So I can write that equation and try and solve it. X over 3 equal to 2. That's an equation. I know that it has to be 2 to get 4. All right, so this seems good. This seems true. Now I want to think to myself, can I solve this? My goal is to figure out what x is to solve for x. I see that right now it's being divided by 3. So if I want to undo a division, I need to do the inverse operation. Instead of dividing by 3, the inverse is multiplying by 3. Multiply by 3. What I do to one side of the equation, I need to do the same to the other side of the equation. Got to do the same thing to keep it equal. All right. Inverse operations undo themselves. We have a multiply by 3. We have a divide by 3. So that just goes to 1. All that's left on this side is just x. On the right side, we have 2 times 3, which is 6. And I should check myself, right? I should know that if I plug this back in, it should indeed give me 4. So here's my conjecture. X equals 6. I'm going to try it. 2 to the 6 over 3 equal to 4. 2 to the 6 over 3, that's the same as 6 divided by 3 is 2. 2 squared equal to 4. Yes, sounds good. So what we've done here is we've used our rewriting our rationals. We've used our exponent properties to come up with a way, an expression that allows us to see, oh, if I could only figure out what x would be to make this whole exponent equal to 4, and then we kind of used our algebra tools, wrote a small equation help us along the way. All right. This is tying together a lot, but take your time on this one. Pause the video, try it out. I would start by rewriting what you know. I would start thinking about like what needs to be true for it to be 27. And then once you've thought about it, tried it out, we'll walk through it together. So again, hopefully you've tried this out. I noticed right away there's a square root here. There's a radical sign I'd like to rewrite. Like we said at the beginning, when we have a square root, when we have a radical without a number, we assume it's the square root. We assume it's the second root. So this is radical 3, so square root of 3. We're going to pretend there's a 2 there. So I'm going to rewrite it as 3 to the 1/2 raised to the x equal to 27. All right, I'm actually going to go a step further here. I'm going to use our exponent rules right away. 3 to the 1/2 raised to another power. That means we have to multiply these. So I'm going to multiply those. 3 raised to the x over 2 equal to 27. All right, so all we've done is rewrite this with radical exponents. Now I got to start thinking to myself, boy, what does my x need to be equal to make this true? Well, if I just need to know what this whole exponent needs to be. 3 to the what power gives me 27. In other words, it's asking 3, let's see if we can come up with this. 3 times 3, 3 squared is 9. If that's not enough, we need to go more. So maybe it's 3 to the third. 3 to the third equals 3 times 3, which is 9, times 3. 9 times 3 is 27. Okay, so now I took some time to figure it out. I need the exponent on 3 to be 3 overall. Right now it's x over 2, so I just have to figure out what x makes that true. So I'm going to rewrite this actually again. I want x over 2 to be equal to 3. Those need to be the same to make it 27. So I'm going to write that simple equation up here. X over 2 equal to 3. X over 2 equal to 3. Just like before, we have a one-step equation. I see here it's being divided by 2 instead. To undo a divide by 2, I'm going to multiply by 2. Dot. I like the dot. Multiply by 2 on both sides. When we do to one side of the equation, we have to do the other to keep it equal. Divide. X equals 3 times 2 again, 6. Great. So here, we used our rules, we rewrote it, we identified what this exponent needed to be, and then we used that to write a simple equation and solve. So that's pretty much the scope of what we're going to do in this lesson. Things to be aware of with this. These are pretty straightforward. They're just applying your rules on the front page. Down here, we're starting to combine multiple rules. So like we have radical exponents, and we also have, we have radicals, and we also have exponent rules that we're going to have to combine, maybe working with some fractions. On the back side, there are continuing to practice the multiple rules, and then your mastery check is at the bottom, right? Mastery. These are the 4 problems you need to do independently. 2 of them you're solving for x, 2 of them you're just simplifying the expressions. All right, good luck with this. Ask your intervention teacher if you have any questions, talk to your peers, and I'll see you all next time.